My name is Evgeny Gusev. I'm from Qualcomm AI Research, and I will be the moderator for this keynote session. It is my pleasure to introduce our first keynote speaker. It's Blair NEWMAN from Neuton.ai, which is a project of a Bell integrator company. And Neuton is the Chief Technology Officer there. So Blair has over 20 years of experience in this industry, and he has a successful track record of leadership through different projects and companies. Prior to Neuton, he held various leadership positions and role at T-Systems North America, which is a division of Deutsche Telekom, and he was responsible for strategic directions and for leadership in the areas of compute and applications and infrastructure. So I think what he's going to talk today is actually very interesting, how to build very, very tiny models for machine learning using the new novel approach. I think we are really excited to see these results. And Blair, the stage is yours. And again, the reminder: please use the Q&A button at the bottom, and I think we'll get to the questions at the end.
All right, thank you, Evgeny, for the introduction and kind words, and of course, thanks to the entire committee for giving us the opportunity to share our new solution called Neuton. So by way of introduction, just again, my name is Blair NEWMAN. I am the CTO here at Neuton. We're based in San Jose, California. So I know that for most of you, it is in the afternoon, and for myself, it's in the morning. One of the things that I kind of like to begin to kind of start out with is that our mission here at Neuton has always been to bring machine learning to everyone. And when we had the opportunity to begin to work with the TinyML community, I know one of the goals that was shared to myself, that I know that Evgeny kind of speaks about fairly regularly, is how can we make TinyML everywhere, right? How can there be millions of different devices that are enabled intelligently? And one of the things that we appreciate, or I appreciate, is that the community here from a TinyML perspective covers a number of different areas, a number of different demographics. So we have some resources or some people who are on the call that may be new to edge computing, may be new to TinyML. I'm sure we also have some seasoned and more experienced resources from a data science perspective. And then of course, we have some individuals on the business side that is beginning to take a look at how can machine learning, how can TinyML be applied to their business so that they can begin to drive value out of it. And that really, from my perspective, it really overlays really nicely with Neuton, because as I mentioned, our objective is truly to make machine learning available to everyone. But specifically, when we began to talk about TinyML, there's a couple of different things that come to mind. One is, how can we begin to bridge this physical world with the digital world? And that's really the basis of TinyML. And when we are discussing Neuton, we certainly believe that we're not only that missing link that can begin to bridge that physical world and digital world, but more importantly, that we can accelerate it. So that's really our mission, is to how can we really accelerate TinyML throughout the community, not only from a technical perspective, but also from a business perspective as well. And one of the things that we'll be looking to share with you guys today, we call it a novel approach. We'll really kind of share with you guys a different approach that we're taking to machine learning and that we're taking to TinyML, that we believe that all of you guys will get a tremendous amount of value out of. So when we kind of begin to look at or think about, let's say, the journey today, specifically for this discussion, we're going to take a couple of different steps as we go throughout today's discussion. The first is what I like to say is called what is. I think it's very important that we kind of level set on different let's say, terminologies, how AI is looked at today, how machine learning is looked at today, how edge computing is looked at today, and of course, how TinyML is looked at. But then also the whatnots. What's preventing the acceleration of TinyML throughout the community? And then what I like to call the what ifs, some of the things that maybe a year ago or 2 years ago, when TinyML began evolving, that we wish that we could accomplish. And then the what next. And the what next is what I like to say will be the meat and potatoes of today's discussion, where we'll share with you guys some really new, disruptive, and innovative approaches to building tiny models. So that's what our journey will look like today. So starting first with the what is. Of course, there's artificial intelligence. And artificial intelligence is, of course, it's a very broad stroke or very broad term. A lot of people, a lot of individuals, a lot of organizations, sometimes they struggle with defining AI. They say, hey, we know, or they understand that they need to begin to incorporate this technology into their ecosystem, but oftentimes they have trouble being able to accomplish this. And that's where we begin to get into machine learning. And of course, in addition to machine learning, there can be deep learning, et cetera. But one of the things that we are here to discuss today is how we can begin to bring this intelligence to the edge. And we're going to cover this not only from a technical perspective, but also from a business perspective, because in order for TinyML to really begin to proliferate, let's say, throughout the world, we need to take some key steps to not only ensuring enablement from a technology perspective, but also enablement from a business perspective as well. And we're going to cover that entire life cycle in today's discussion. So let's go to now the whatnot. What are some of the barriers that we've seen that is posing challenges from a TinyML perspective? What is hindering that adoption? What is hindering that acceleration? When I hear the community talk about, hey, how can we have millions of intelligent devices out there? One of the main barriers that are out there is really just the limited amount of resources that are available that can actually successfully implement a machine learning model. But TinyML, I'm sure as you guys know, it covers multiple ecosystems. It not only covers, let's say, machine learning from a machine learning perspective, but also it covers hardware perspective. And then it also covers the integration of those two different technologies. And it's very unique because typically you need multiple different skill sets in order to implement the entire life cycle of TinyML. Then, if you do have those multiple skill sets and you are able to actually produce a model that is meeting your business requirements, now can you successfully implement or integrate that model into that hardware device? And that's something else that we'll be looking to we'll be looking to discuss and cover today. And then from there, once you're in production, how do you know that your model will actually perform as expected? How do you know that it has the quality that you would expect? How do you know that the predictions that you're actually making is actually what your model should be doing? But then after that, how do you know when you need to retrain your model? How do you know when your model may be decaying? And that's another thing that we'll begin to address from a TinyML perspective, is how we're also bringing forward explainability as well. So one of the things that I like to do is kind of invite all of you guys maybe to even make your own list as I go through these next couple of slides. And this is what I call what if. What if you could build a model without having any technical expertise? What if you can not only build that model, but you can also integrate that model without having any technical expertise, or very limited technical expertise? What about if you could build a model in 3 clicks and have that model ready to be embedded after those 3 clicks? What about if you could actually build a model, an optimal model, in one iteration? So you go through one iteration, you have the most accurate model, you have the most compact model, and you're able to explain each prediction along the way. What if you could do that? What about if you could produce a model that was 1,000 times smaller than what you're doing today? If you're using Tensor Flow as an example, or Tensor Flow Lite as an example, what if you can produce a model in one iteration that is 1,000 times smaller than what you're accomplishing today? What if you can run inferences up to 60% faster after that one iteration? Would that be something that you would be interested in? What about in that one iteration, you could eliminate the need to perform any compression? No pruning, nothing, and not compromise accuracy. Would you find that interesting? What about if you can explain what is driving every single prediction that your model makes? What about if you could accelerate your time to market by 85%? From a business perspective, would that be something that you would be interested in? What about if you could build fast, you could build once, and never compromise accuracy or your requirements along the way? Just take a moment to think about some of those different things. And one of the things that we're going to do is we're going to show you how you can accomplish all of those steps along the way by using our platform. So what's next? One of the next things that I would like to share with you guys is how we're doing things today. What's the typical approach that is typically taken in order to implement a TinyML solution? More often than not, at least we like to think so, that we typically start out with some business requirements. We actually want to implement a particular solution. We then, from there, we go through and we identify the hardware, we identify the sensors that we need in order to facilitate that solution. We're keeping in mind what's our power consumption. We're keeping in mind, how much memory is available on that particular device. And then from there, we say, okay, we have our requirements. We've identified our hardware. Now let's go through, let's create a model, right? We start this manual process of building our model. Using a framework or tool of your choice, you then go through several iterations. And sometimes, if you're lucky, you don't have to go through a lot of iterations, but typically you go through a number of different iterations in order to produce a model that you find acceptable. Then you come to the next task. Now that you've created this model, you have your hardware, and you say, all right, how can I put this square peg in a round hole? How can I make this model now actually successfully integrate into the hardware that you've identified? So then you go through a number of different steps, whether it's pruning, whether it's quantization, et cetera. You go through those steps, and then finally you get to a point where you have identified, you have a model that you can now actually embed into your microcontroller. Hopefully it still has the accuracy that your business requires or that your use case requires. And then from there, you embed into your model. Everything, hopefully at that point, is great. If not, you have to start over. But then you finally get to the point where you say, okay, I'm ready for production. But then you have to ask yourself, can you actually trust that model? Will it actually perform up to your business requirements? And typically this process is normally manual. And of course, there's different tools that you can use to help accelerate it to some degree. But in the end, you're still left trying to understand if whether or not the model that you've produced and that you've integrated into your hardware device will perform up to your expectations. But then also you must ask, when do I need to retrain my model? When is my model decaying? This is how things are done today. So what I'd like to share with you guys now is how we can flip this paradigm completely on its head. And that's where Newton comes into play. Our solution allows for you to build fast, build once, and never compromise your accuracy or your requirements along the way. Newton is the start of the true democratization of TinyML. Our platform is a zero-code solution that enables anyone to build a model in one iteration without compromising accuracy. And how do we do that? I'll go into detail in just a moment, but one of the things that we actually do is every model that we build is fit for purpose. We build every model neuron by neuron, one neuron at a time. We don't start with an existing framework and then scale down from there. So our approach, our target, in order to help accelerate and democratize TinyML, is our platform, Newton. And in doing so, what we're able to see and help our customers realize is that the models that they're producing are 1,000 times, hundreds of times, more often than not, smaller from a coefficient and neuron perspective. In size, they have faster inference times, and of course, they're obviously going to consume less power in comparison to the tools that many of us have been using today, which of course includes Tensor Flow, Tensor Flow Lite, as well as other algorithms that are out there. And in doing so, we're not compromising any accuracy along the way, even though our models are extremely compact. Now, how do we do this? Let me begin to show you. I will play a video to begin to introduce how we take this approach and how we accomplish this.
How does Newton create incredibly compact and accurate models? First, Newton uses a selective approach to the connected features. Let us take as an example, the model for determining cardiac arrhythmias. Amplitude of contraction of the heart muscle acts as one of the features for training the model. As you can see, Newton only needed to make connections with half of the features. We also leverage a unique patented algorithm to adjust the coefficients within a model. Unlike most algorithms, Newton's algorithm is not based on backward propagation of errors and the stochastic gradient descent. Furthermore, the Newton algorithm is minimizing the likelihood of hitting local minima. This is especially important when building small models. You can see that in our example we've achieved an area under the curve value of 0.96 with only 253 coefficients. Meanwhile, achieving the same accuracy with TensorFlow requires significantly more coefficients. Newton is even 10 times smaller than TensorFlow Lite. The Newton platform enables models to be built automatically, neuron by neuron, starting from learning general features and moving toward identifying the most specific ones. This allows selection of a model of almost any level of precision and size, in a single iteration. The Newton eliminates the time-consuming multidimensional manual search for network parameters including number of layers, neurons, type of activation function, batch size, dropout, learning rate, and more efficiently finds the optimal structure. The neuron by neuron growth makes it possible for cross-validation to occur progressively, which is typically not feasible with a standard approach. The combination of these characteristics also increases the generalizing capabilities of the model, which allows for creation of compact models, without compromising accuracy.
Okay, just give me a second to come back to the presentation. So if I may, I'll just quickly summarize some of the things that we just shared in the video. As mentioned, when we build our models, we don't start out initially with an existing framework and then go from there. When we build our models, we take a very selective approach, only connecting to the features that are deemed most important to creating an accurate model. When we do build out our models, all of our models are built automatically, neuron by neuron, optimizing and validating the quality of the model along the way. And our models are subsequently self-growing and self-learning. So typically, when you're building a model, you have to go through that iterative process, searching for and trying to validate the various features that allow for your model to reach or achieve your goals. Our algorithm, which is something that we've developed internally in-house, eliminates those needs or those iterations that you would typically have to go through. So in one sense, we're automating our entire solution. And we'll show you in just a moment how you're able to accomplish that without leveraging any technical skills, being able to create those models in 3 simple steps. In one iteration, you're able to have a highly accurate model with never compromising accuracy along the way. So, taking just a step back, when we again take a look at how we got to where we are today, and of course, TinyML over the last couple of years has been accelerating. I think this week's event is a testament to that, where we're able to see the adoption of TinyML really continuing to accelerate and really continuing to grow. But when you look at how models are being built today, there's a number of different variables that you oftentimes have to take into consideration in order to produce those models. Oftentimes, you're starting with a predefined architecture or structure, and typically, defined by someone, and you're applying those methods when you're looking to identify that model that is reaching those requirements that you've set forth. In regards to our solution, only our neuron parameters actually undergo optimization as we build the models along the way. So instead of taking the approach of having a predefined structure, building a model, and then optimizing that model so that it can actually meet your requirements, we take a bottoms-up approach. No longer having to deal with unnecessary growth as it relates to your model or your network size. So our future today, what we're doing from a Newton perspective. As I mentioned, our solution is not based upon some of the standard approaches that are used today, whether it's backpropagation, whether it's stochastic gradient descent. We limit or eliminate the problems associated with local extremes and plateaus. We help improve the efficiency of each neuron, and we reduce, which allows for us to ultimately reduce the overall network volume. Taking this approach allows for our solution to have a significant amount of potential as it relates to parallelization, And as we're building our models, it allows for us to have permanent cross-validation. Our models, as we are building those models, neuron by neuron, also includes overfitting control along the way. So our models build dynamically, which allows for us to achieve the most maximum generalization ability. Ultimately resulting in a model that is extremely compact and is allowing for you to reach your requirements in one iteration. So as I mentioned, we eliminate the need or the necessity to perform any network architecture searches that you may typically do today. We're optimizing, our optimization occurs neuron by neuron as we build the model. And we ultimately don't require the need for quantization, pruning, or distillation, which ultimately allows for us to not compromise accuracy along the way. So what does this do? This allows for our solution to be embedded into any microcontroller. So we don't have any limitations with our platform as it relates to which devices our models can actually successfully integrate with. We're able to integrate into devices that may have, let's say, less than 100 kilobytes of memory. So our solution allows for our customers to not be defined by hardware, because our solution can actually build the models, and you can define along the way which size of the model you would like or that meets your requirements. And once training ends, then you will know that you'll have the most accurate model based upon the size that your requirements require. As we go through each iteration, we perform cross-validation to ensure that you have the most stable, the most accurate model at that point. Next, I'll show you in detail a specific use case that we've just recently worked on. And we'll explain as well, and you'll see how our platform actually works in action.
Let us take a look at an example of a model used to determine cardiac arrhythmias from cardiogram data. We would like to leverage the created model to predict whether there is an impending arrhythmia or not by running inferences on the microcontroller, without sending the corresponding sensor data to the cloud. During this process, we will show the complete life cycle from training, leveraging Neuton platform, to successfully embedding the model in a microcontroller. In addition, we will show the same process while leveraging Tensor Flow. So, in order to train a model on the Neuton platform, you must simply load a CSV file with historical data, in this case various cardiograms, where arrhythmia is noted. The file contains more than 11,000 rows, amplitudes of contractions of the heart muscle act as features for training the model. We select the appropriate task type and target metric. Neuton provides a number of settings to work with microcontrollers. In this case we choose 8-bit depth support, then we start training. At this point everything else happens automatically. Our manual effort to get to this point is minimal at best, oftentimes less than 2 minutes. At this time the training on the Neuton platform has concluded. Upon completion we have realized the following model characteristics: area under the curve equals 0.96, a model size of 0.7 kilobits, and with the number of coefficients totaling 253. This is an excellent result. Now our model is ready to be embedded into a microcontroller.
So I'd like to just take a moment and just stop here briefly and just really give an overview, a highlight what you just saw. When leveraging our platform, one of the things that I highlighted is that our pipeline to build models have been streamlined into 3 steps. The first step being you upload your data. The second step being that you identify your target variable. And then the third step being that you start training and then predictions are enabled. So that's the workflow that you typically will follow when it comes to using our platform. What we're going to show now, just for comparison's sake, is what are the steps that historically we have taken, or maybe that you're even taking today, just so that we can see how we're taking the next step forward into enabling machine learning, enabling TinyML for all, but also enabling the TinyML community to begin to do something different, disruptive, and innovative.
We begin building a network while leveraging Tensor Flow. We first begin by looking for the optimal architecture while also looking to sort out the associated parameters. Here are a list of other potential settings that must be handpicked and validated. This is a long, random and laborious process that does not guarantee finding the optimal structure. We will show the example and results if just one of the many available parameters are selected for the given network architecture. This absolutely cannot be done without special training. In addition, we must spend several hours iterating over these parameters. We begin by initializing the network with one hidden layer, after which we will train and validate the model. We have set aside 20% of the training data as a holdout set for validation. Now that the network is trained and validated, we can see that we have achieved a model accuracy of 0.857 measured with the metric area under the curve. This now becomes our baseline. Let's add one more hidden layer and see if it will improve our results. To see the updated results due to our changes, we must train and validate the model once again. As a result, we can now see that our accuracy has increased significantly, and the measured metric has increased up to 0.96. Let us now change the activation mode of the previously added layer from ReLU to TANH and see what happens. As we know, this is a random and iterative process that occurs when building a model. We now see that our result has decreased in comparison to the previous iteration. Let's discard the activation change from the last step, since ReLU clearly provides better results. Again, taking another step in the iterative and manual process of model building, we will now add another 3 hidden layers, all with the ReLU activation function, and see if this will improve our metrics. We can see that our new score is now 0.956, which is a clear indication that our resulting model is overfit. Let us now once again change the activations of the previously added layers to TANH. In this case, we can see that our model got stuck in the local minimum. This time, let's change the activation of just one hidden layer from TANH to ReLU. We can see that our model has once again experienced overfitting. After reviewing the previous 2 iterations, we can easily draw the conclusion that our model from 2 steps ago produces the most optimal results. Here is summary of all the differing and necessary steps we took in order to identify the most optimal model. After several hours of iterating over various parameters, we created a model in Tensor Flow with similar characteristics as it relates to model accuracy. However, the model size is indeed much larger than the results we would typically see with Neuton. Neuton's model is 47 times smaller than Tensor Flow. However, you cannot embed model immediately. We need to reduce it using the TensorFlow light converter. We can see that the firmware does not fit into the flash memory of the targeted microcontroller. Therefore, by reducing the list of operations that the interpreter supports, you can reduce its size. In order to accomplish this, we must open the main_functions.cc file and change all ops resolver to micromutable op resolver. Our model requires only 5 operations. Compiling it, we see that the size has decreased. But Neuton's model is still 10 times smaller than TensorFlow Lite model. Now our model is ready to be embedded into a microcontroller. Next, we proceed with opening the archive folder for microcontrollers, which contains all the necessary files, which simply can be transferred to the microcontroller's firmware project. Now to compile the project, we need to press the build button. After the compilation is complete, we then press the debug button. The program will then proceed to be loaded into the microcontroller. Click Stop. Everything is ready to run inference in the microcontroller. Next, we take data from a digital cardiograph as input data and transfer it to a microcontroller. If the red light comes on, then an arrhythmia is detected during the reading. Now we see that the green light has turned on, which tells us there is no arrhythmia detected with this particular reading. We see that the light has now turned red once, which tells that everything is once an anomaly within the reading has been identified. We perform similar operations for the Tensor Flow light model. As we can see, most of the time was spent on manually selecting the neural network architecture, selecting parameters and converting the model, compressing it, and reducing the number of operations. Now let's summarize the results. We see that with the help of Neuton we managed to automatically, just in one iteration, build a model that is 10 times smaller than even TensorFlow Lite. It utilizes 3.5 times less RAM. It demonstrates 2.5 times faster inference time. We also considered other comparable solutions such as Edge Impulse, which has TensorFlow Lite under the hood, however eliminates the usage of an interpreter to decrease memory usage and inference time. Nevertheless, we still experienced lower model accuracy and increased inference time and still a materially larger model size than Neuton. And most importantly, working with Neuton does not require any special qualifications and implies little human effort to launch similar projects. Neuton's model allows predictions to be made at 2 milliseconds, which is almost 460 times faster than the average heart rate.
So definitely a lot to unpack there, and I'll just kind of quickly summarize. One of the things that we wanted to show and demonstrate was the process and the workflow that you would typically follow while using our platform. As I've mentioned, our platform is streamlined into 3 distinct steps, which I'm sure, as you guys know, typically when you're building a model manually, it's typically a much more longer and laborious process that you typically have to go through. It's also typically a very iterative process that you have to go through in order to achieve and reach some of the goals that you may have outlined. And even then, if after you do go through that process, sometimes you're not able to achieve the results that you're looking for, whether it's in model size or whether it's in model accuracy. And that's where, of course, where historically we've had the opportunity to use TensorFlow Lite in order to reduce that model size, oftentimes at the sacrifice of our requirements. You're taking more often than not that top-down approach in order to build a model, where with Neuton, we're taking a much more bottoms-up approach, building those models neuron by neuron, never requiring at any point to have to apply any of those additional techniques so that you can get the model size to meet your requirements from a hardware perspective. A lot of times that requires a number of different skills in order to produce those results. Since we have an automated solution, we've really reduced those skill profiles to where sometimes it requires 3 to 4 different skill profiles. Well, with our solution, it oftentimes just requires 1. Now, what are we doing today? We did show you or highlight to you one of the use cases where we're using some sensory data, but I also kind of wanted to give you guys an overview so you have a better understanding of the platform's current capabilities and where we're going to in the future. Right now, our solution is solving regression problems, time series problems, classifications, classification problems, binomial and multinomial, as well as NLP. This year, we're also doing audio, and heading into next year, we'll be adding images as well as video to our solution. So we're certainly expecting that in the near distant future, our zero code AutoML solution will be addressing all of these different problem types. But yet again, we've now produced a model, it's in production, but what's next? This is where I like to highlight myself, the 4 W's. These are the 4 things you should always be asking yourself. Number 1, of course, what does your data consist of? What features are actually important to your model that is actually influencing your predictions? Why does your model actually make certain predictions? And of course, when should you retrain your model? In our platform, we provide an exploratory data analysis tool. We have an extremely robust explainability office, starting first with the EDA. Then we have our feature importance matrix. It helps you understand what are the top 10 features that are impacting your predictions. But it also lets you know what are the bottom 10 features that are not influencing your predictions. A lot of times our customers, they think or they believe that there's certain data points that are driving predictions, but in reality, they're not. So we provide this insight. But what I'm really excited about is helping you understand why your models are making certain predictions. One of the tools that we provide is a model interpreter. This tool allows for you to dynamically change the values of your features to see how it influences your predictions. So you can independently go through and dynamically change the value on the fly, each feature, so that you have insight as to what's actually driving your predictions. We're super excited about this tool. And then the model to data relevance indicator. It's a very long word, but in short, it lets you know proactively when you should retrain your model, when your model is beginning to experience decay. We do that proactively. I just wanted to give a brief overview on that because later on this afternoon, we'll be having a session where we'll go through our explainability office in much greater detail so that we enable you, we empower you to have insight as to what is actually underneath the hood. Now, beginning to summarize, at the beginning of the discussion, I began to highlight a number of different what ifs. And some of those what ifs were, can you build a model without having any technical expertise? Can you create a model in just 3 clicks? Are you able to build a model, an optimal model that is compact and accurate in one iteration? Are you able to produce models that in some cases are 1,000 times smaller than what you are using today with Tensor Flow Lite? How can you be enabled to run inferences up to 60% faster? Eliminate the need to perform any compression techniques without compromising accuracy. Explain how you can make and understand every single prediction. And of course, accelerating your time to market. That's why we take the approach of building fast, building once, and never compromising your requirements or your model accuracy. So we began this discussion highlighting what are some of the challenges that are inhibiting or preventing tiny ML from being in millions of devices, billions of devices. It's the availability of technical resources, data scientists, the challenge that we have regularly. Can my model fit into my hardware device, especially as they continue to get smaller and smaller? But then once you're in production, understanding the quality behind your model, understanding each individual prediction, and being able to proactively identify if your model is beginning to decay. With Newton, we believe that we're solving all of those problems right now. Our platform is available for use for the data scientists, for the non-data scientists alike. All of the models that we build, all of them, are built for purpose, neuron by neuron. We never start off with a pre-existing structure. And once those models are built, you don't have to compromise accuracy by going through and performing any compression techniques. And then lastly, once you're in production, understanding what's behind your models, understanding when you should maybe take the next step and retrain your model. So as I wrap up, I'd like to once again extend my thanks to all of you guys for having me during this session. Hopefully, I had the opportunity to share with you guys some issues or some challenges that you were experiencing prior to today. And I encourage you guys to come to our next session, which will be going deeper into explainability. So once again, thank you for having me. And I'll hand it back to Evgeny.
Well, thank you, Blair, for this very interesting presentation, actually quite amazing results. And thank you also for opening up your secret source platform for the very first time at the TinyML forum here. So there are like an overwhelming number of questions on the chat. There are like 33 questions on the chat. So we won't be able to answer all of them, but I've been monitoring them as you spoke. So maybe I can summarize some of them in groups. And I think the good news is that in 2 hours, we are going to have time for Q&A when you have your session on explainability. So the key questions there, if I summarize them,
hold on, Evgeny, I'm sorry. Bert, would you please unshare your slides until okay, back to you, Evgeny.
So the results you share there, they're very good. So the question is, what are the trade-offs? What are the limitations of your algorithms? I mean, you mentioned some of the use cases, cardio, then you're going to work on audio, video. Are there any limitations? Because we know there is no such thing as free lunch. What are the trade-offs when you develop your models?
Are you saying trade-offs from an accuracy perspective, or trade-offs as relates to being able to integrate with into different devices?
Mostly from the accuracy, like when you design your models.
Quite frankly, we don't have any, no trade-offs in this particular case, because just the approach that we're taking really doesn't afford us, or really doesn't require us to compromise on accuracy along the way. And one of the ways as to how we're accomplishing this is that as we are building the model, each iterative step, and in our case, an iteration is actually adding a neuron. So every time we take that iteration, we actually perform some cross-validation along the way. So as it relates to accuracy, in a real sense, we don't compromise.
Okay, that's good. Second kind of group of questions in terms of using your approach with specific hardware. What kind of microcontrollers people can use to try your approach and develop real world applications?
Yeah, so far we haven't ran into any limitations as it relates to not being able to successfully integrate into different devices. So our platform is not designed so that it operates with specific microcontrollers. So for all intents and purposes, our models are able to successfully integrate into a variety of different microcontrollers. So I know that there are some tools that are really geared towards specific devices or microcontrollers. Our platform is not, we're not building models specific to different devices.
Okay, thank you, Blair. And I'm going to conclude with this question because I'm sure there are people in the audience who would like to try your approach and play and develop their own tools. And there was a question like, hey, TensorFlow is an open source platform, people can get it. How can people get your platform and start doing evaluations and developing applications? What do they do?
I'll narrow it down to 2 steps. You can go to Neuton.ai. Once you go to Neuton.ai, there's an opportunity to sign up and leverage our platform for free with our Gravity plan. So you go to Neuton.ai, you sign up for the free plan, and you can use our platform. And you can actually use all of the functions that you've seen today. So we don't scale our functions from one plan to the next. So our free plan offers all of the functionality that I began to share today.
Great. Well, thank you again, Blair. There are like 35 questions on the chat, so it's overwhelming.
This would not be made possible without our sponsors, whom I would like to once again express our gratitude, starting by premier sponsor Neuton.ai. Thank you guys so much. The executive sponsors, which involve ARM, Edge Impulse, Qualcomm AI, and Sentient. The platinum sponsors, which involve Infineon, Reality AI, the gold sponsors, which involved Latent AI, SenseML, and last but not least, our silver sponsors, which involve EMSA, Greenwaves, Kixo, Imagimob, HOTC, Seed Studio, and ST Microelectronics. Thank you, everybody. See you all tomorrow with more exciting features.